This is our last chapter that we need to do before the final exam. So chapter 7 is all about conic sections. And when we are talking about conic sections, we're basically talking about, as you can see in this image right over here, when you take a, I was trying to think what it's called, a double right circular cone. So when you take a double right circular cone and basically intersect it with the plane, so that intersection, as you can see, will cause different shapes depending on how you are intersecting at what angle. So you can create a parabola if you just take one of those right circular cones and intersect it with the plane at an angle. You will create a circle if your plane is going to be intersecting basically, horizontally right at, you can kind of think of at 180 degrees, you will create a circle. If you change the angle of that plane just slightly, you will create an ellipse. And as you can see, when that plane is intersecting both the top and the bottom right circular cones, you create a hyperbola. So these are going to be the 4 different conic sections that we are going to be looking at. And obviously, since these curves are created from these right circular cones, that's the reason why we call these guys conic sections. So they are saying if the plane passes through the vertex of the cone, then the intersection of the cone and the plane is called a degenerate conic. And when we're talking about the vertex, that's of course going to be right where those, the tip of the 2 cones is going to meet. So if you actually click on this image over here, it takes you to this video over here for conic section. So before we actually get started, I kind of wanted to show you part of this video. So we'll take a look at that and then we'll come back to our handout over here. Okay, so let's take a look at this.
Conic sections.
Oops.
In this module, you will learn about conic sections. When a straight line intersects the vertical line at a fixed point and rotates about that fixed point, the surface obtained is called a double right circular cone. A double right circular cone consists of 2 cones joined at a fixed point called the vertex. The line that rotates about the vertex is called the generator, and the line that remains fixed is called the axis. A right circular cone has a circular base, and its axis is always perpendicular line from the center of the base to the vertex. The perimeter of the base is called the directrix. The lateral surface of a right circular cone is called a nap. A double right circular cone has 2 naps. The nap above the vertex is called the upper nap, and that below the vertex is called the lower nap. Also, the angle between the generator and the axis is called the vertex angle. Conic sections. If a plane intersects a double right circular cone, we get 2-dimensional curves of different types. These curves are called conic sections. Depending on the angle made by the plane with the vertical axis of the cone, the plane can cut the cone in 3 different ways. Ellipse. When the plane intersects the double right circular cone in such a way that the angle between the plane and the axis is greater than the vertex angle, we get a closed curve called an ellipse. When the plane is perpendicular to the axis, the ellipse becomes a circle. Thus, a circle is a special type of ellipse. Parabola. When the angle made by the plane to the vertical axis is exactly equal to the vertex angle, we get an open curve called a parabola at the intersecting surface of the cone. Hyperbola. The plane intersects only one half of the double wide circular cone as long as the angle between the plane and the vertical axis is greater than or equal to the vertex angle. However, if the plane intersects the vertical axis at an angle smaller than the vertex angle, the plane intersects both the halves of the cone to form an open curve called a hyperbola, which has two disjoint curves. These generate conics. If the plane intersects the double wide circular cone at its vertex, the ellipse becomes a point, the parabola becomes a line, and the hyperbola becomes two intersecting lines. The figures so obtained are called degenerate conics. In this module, you have learned that when
Alrighty, guys. So just a quick video on, what the conic sections are. Now, we have talked about parabolas and circles in our previous chapters, but, obviously we did not really look at them in terms of these conic sections. So your definition is going to change a little bit, as we are going through these different conic sections over here. So in 7.1, we're actually focusing on the parabola. In 7.2, we'll talk about the circle and the ellipse. And then in section 7.3 is where we talk about the hyperbola. So each of these are going to be distinct from one another. The one thing we definitely want to keep in mind, if you look at those curves on the hyperbola, they might kind of look like parabolas, but by definition, they are not parabolas. They may have that similar shape, but as you saw in the video, as they were explaining, it's a difference between what kind of angle the plane is making with that, vertical axis for the circular cones. And then of course your ellipse and circle are actually in the same category because your circle is just a special type of an ellipse. So, these are the different things we will be looking at. Now, so far when we studied parabolas, we of course talked of them in terms of their algebraic definitions. So we know in the standard form, a parabola has the equation y equals ax squared plus bx plus c. And of course, we don't want our a value to be equal to 0 because that x squared term would disappear. And then we also saw what I call the transformation form. So we saw the transformation form of parabolas in chapter 3. So that is y equals a times the quantity x minus h squared plus k. And so we are familiar with both of these equations for our parabola. Now, when we are talking about the geometric definition, which is what we're looking at here with these conic sections, you don't actually have an equation for this, but the way we define a parabola in the geometric definition is, as you can see, a parabola is a set of all points in the plane that are equidistant from a fixed line, which is what we call as the directrix, and a fixed point, which is not on the line, which is what we call as the focus. So if you will look at this little graph over here, you can see in the red, we have our parabola. Above the parabola, you have your fixed point, which is the focus. And below the parabola, we have the fixed line, which is our directrix. Now, the key thing to remember here is that this distance between the focus and the vertex and the distance between the vertex and the directrix is actually going to be same. So that distance from the parabola's vertex, and remember the vertex is the lowest point on your parabola if the parabola is opening up, or it's going to be the highest point on your parabola if the parabola opens downward. You can see the axis of symmetry. And again, from chapter 3, you should remember that the axis of symmetry passes through the vertex of our parabola. So what's going to happen here is, in terms of the focus and the vertex, our axis of symmetry is going to pass directly through both of those points, and your axis of symmetry is going to be perpendicular to the directrix over here. So it's going to make that 90-degree angle between the axis of symmetry for our parabola and the directrix of our parabola over here. Yeah, so they're kind of talking about that right here in this little paragraph, how the axis of symmetry will be perpendicular to the directrix. It contains the focus. When they're saying contains the focus, it basically means it's going to be passing through the focus. And then of course we know the vertex is also going to be a point which is on the axis of symmetry. And like I said, the distance between the vertex and the focus and the distance between the directrix and the vertex is going to be the same. Now, just as some formulas to help us, with these geometric definitions over here, for the focus of the parabola, which is, again, remember that fixed point above the vertex, you can actually use the ordered pair of h for the x value and k plus p for the y value. Now, remember, the original vertex will have the ordered pair hk. So the focus is actually a modification on that. And this p variable that you are seeing here, this p variable is actually talking about this distance between the vertex and the focus, or the distance between the vertex and the directrix. So that's where this k plus p is coming. So if you know where your vertex is at, you can actually calculate where the focus is going to be if you can calculate that distance p. Now this directrix, which would be the, the horizontal line underneath our parabola, that will have an equation. Since it's a line, it's going to have the equation y equals k minus p. And we are also defining the relationship between our a, which is the leading coefficient on our parabola. So the a value can actually help you find what the p value is. So if you know what that a is, you can calculate the p value. Again, remember, p is the distance between the vertex and our focus, or the distance between the vertex and our directrix. And of course, your original vertex, as I said, is going to be at hk. Now, this definition that you are seeing here is based on this transformation form of our parabola. So, if you wanted to transfer this into the standard form, we'll see some calculations on how you can actually also use the standard form of your equation to help you come up with these same definitions over here. Now, something that will kind of help us keep some of these terms in mind is, remember, again, from chapter 3, if your a value was positive, if the a value was positive, remember your parabola was opening up. And if the a value was negative, your parabola was opening down. So since we have a relationship between a and p over here, a equals, 1 over 4p, that actually tells us that both a and p will have the same sign. So if a is positive, that tells us p will also be positive. If a is negative, that tells us p will also be a negative number. Okay, so just keep in mind, if both are positive, the parabola will open up. If both are negative, the parabola will open down. And if your parabola opens up, which is what you're seeing in this left-hand side graph, then the focus is going to be above the directrix, okay? And if the parabola is opening down, which is the right-hand side image over here, then of course your focus is going to be below the directrix, okay? Because all of these properties or characteristics, whatever you want to call them, are going to come in handy, when you start looking at questions like these over here. So this one here is asking us to find the equation of the parabola, and they are giving us where the focus is going to be and where the directrix of our parabola is going to be at. So let's try and see, okay, if they're giving us this information, how can we work backwards to come up with the equation of our parabola over here. So we are given the focus is the ordered pair 3, 5, and the directrix. Remember again, the directrix is a line, so you're always going to be given an equation. So we have our focus, we have our directrix. So if you just try to graph this, and you can do just a rough graph, it will actually tell us, depending on what the position of the focus and directrix is, if our parabola is going to be opening up or down. So we're looking at 3 and 5, so that's 1, 2, 3, 1, 2, 3, 4, 5. So this is where the focus is going to be, and the directrix is the line y equals 2. So that's going to be the line y equals 2 right over here. So as you can see, my focus is above the directrix. And remember, this only happens when your parabola is opening up. So that tells us a bunch of stuff. Our parabola opens up. So since it opens up, that tells us our A value has to be positive, which also tells us our P value has to be positive. And remember, P is the distance between the focus and the vertex, or the distance between the vertex and the directrix. So this is something that will come in handy as you are working through these examples. So the first thing we actually want to find out is, what information we can get out of these focus and directrix values. So again, we're going to go back to the definition. They told us the focus can be defined as h comma k plus p. So the x coordinate gives us the h value, the y coordinate gives us k plus p, and then remember, for the directrix, we have the equation y equals k minus p. So you are getting y equals k minus p from the directrix. So if you just take all of that information together, we have h equals 3. We have k plus p equals 5. That's coming from the focus. And then the value of k minus p is equal to 2. So, we just got done talking about system of equations in the last chapter. So you can actually use system of equations right here in these two equations, I guess, is almost what I would want to call them, because you have k plus p equals 5. You have k minus p equals 2. If we just add these equations as it is, you do have that positive and negative p. So you can see how those two numbers would just cancel out, leaving us behind with k plus k, which is going to be 2k. 5 plus 2 would give us 7. Divide both sides by 2, and you end up getting k as 7/2. So you can see now we have our h value. We also have our k value, which is 7/2, and that would form, the vertex of our parabola at hk. So that would be 3 and 7/2. Of course, 7/2 is going to be 3.5. So if you think about this, we are going to be at 3.5 is where that vertex of our parabola is going to be. So right halfway between where the focus and your directrix is going to be, because think about it. If the distance between the focus and the vertex and the directrix is the same, then basically, if you think about, and I'll show it to you here, if you think about this total distance, basically halfway between that is where you should have your vertex. So if you remember that, it would again help you in your calculations over here. So what we are basically trying to do is come up with the equation for our parabola. And right now, what I am actually going for is, since we have the focus and the directrix, it's easier to come up with our equation of the parabola in the transformation form, because we can find the value of h, which of course comes from this x coordinate of our focus. We were able to find the value of k by taking this information of k plus p equals 5 and k minus p equals 2. We were able to solve that and come up with k equals 7/2. So you can see we've already found k, we already knew h. So now the only thing remaining to find in this equation is that a value. And remember the relationship between a and p. They told us a equals 1 divided by 4p. So we can use that information to help us come up with what this a value is going to be. So a equals 1 divided by 4p. Obviously at this point, we don't know what the p value is. But again, coming back to this equation, system of equation that we just solved, if you know the k value, you can go to either one of those two equations and find out what the p value is going to be. So, we can take that first equation, k plus p equals 5. We know k is 7/2. So plug that in and then find what that p value is going to be. So we go ahead and subtract 7/2 on both sides. And what will we end up getting for p when we try and do 5 minus 7/2? What do you think this answer will come out to be? Alrighty, very good, Jack. You got 3.5 over here. So yeah, we are keeping our answers in fractions. If you want to use decimals, you can, but then convert them back into fractions, because they will not accept a decimal answer in my math lab. The other thing you can do is just find your common denominator. So you would end up getting 10 over 2 minus 7 over 2. Keeping that common denominator, of course, you get 3/2. So our p value is going to be 3/2, which is actually telling us what that distance between our vertex and focus is going to be. Now that we know the p value, we can calculate our a using this formula over here. So the very last thing we have to do is find that a value. So a equals 1 divided by 4p, which would of course be 1 divided by 4 times 3/2. Since you do have that 2 on the denominator, this 2 can cancel out the 4 over here. So 2 would go into 4 2 times. And you would end up with 2 times 3 on the denominator, which would of course then come out to be 1/6. So your a value is going to be 1/6. So let's see. We've got a equals 1/6. We've got h equals 3 from our focus. And our k, remember, was 7/2. So the equation of our parabola will end up becoming a is 1/6. X minus h is positive, which means you keep that negative sign as it is. So x minus 3 squared plus 7/2. Now this is if they want you to leave your equation in the transformation form. If they ask you to convert it to the standard form, which is your ax squared plus bx plus c, that means we would need to expand this equation out. And I know there are examples in my math lab which kind of go back and forth. Some of them want the standard form, some of them are okay with this transformation form. So let's say if they did want the transformation form, the first thing we would actually have to do is take this x minus 3 squared and multiply it out, so take its FOIL. So you would go ahead and take that x minus 3 squared, do a FOIL on this two parentheses, which would end up giving us x squared minus 3x minus 3x plus 9, which is basically x squared minus 6x plus 9. So you would first have to expand that out. Then we would still have the 1/6 on the outside. But for the x minus 3 squared, now replace that with your x squared minus 6x plus 9 plus the 7 halves at the end. And then, of course, we would then have to go ahead and distribute that 1/6 inside the parentheses. So you would end up with 1/6 x squared. The 1/6 multiplied by negative 6x, those sixes would cancel out, leaving us behind with minus x. So again, just to show you, when you multiply that 1/6 with 6x, 6 in the denominator, 6 on the top would cancel out, and basically just leaving you behind with x, and then of course keeping that negative sign. When you multiply 1/6 with 9, you're basically looking at 9 over 6, which of course can reduce down to 3 over 2. So that would give us a positive 3 halves, and then of course we have that 7 halves at the end. And when you combine the 3 halves and the 7 halves, as you can see, that would actually end up becoming 10 halves, which obviously cleans up into 5. So by the time you get into the standard form, you end up getting 1/6 x squared minus x, and then those constant terms just become a positive 5. So in the standard form, this is what your equation would look like. But again, you can see that a value still stays the same, because this is the same a that you have here and here in this equation. So that will always stay the 1/6. But obviously in the standard form, you don't have the h or the k values anymore, because all of them kind of get absorbed in this definition. So whenever they ask you to find the equation of the parabola based on the focus and the directrix, your first step is actually going to be is finding it in this transformation form. And once you find all of those 3 values, the a, h, and k, once you have all 3 of them, you get your transformation form. But then if they want the answer in the standard form, then just go ahead and expand everything out, multiply, distribute, and convert it into the standard form, and you end up getting, in this case, y equals 1/6 x squared minus x plus 5. Okay. Questions on this one, guys? So those definitions of the focus and directrix are really important, where they're telling you the focus is h comma k plus p, and the equation of the directrix is y equals k minus p, and then of course the relationship between a and p, which is a equals 1 divided by 4p. All of those definitions are going to be important, when you're working through these examples. Alrighty. Let's take a look at this. So now what's happening here is they're actually giving us the equation in the standard form, which is again your y equals ax squared plus bx plus c. And they are saying, okay, so if we needed to identify our vertex, focus, and directrix, we can convert this into the transformation form. So you can take it from the standard form to the transformation form, and then you can identify what all of these characteristics will be, the vertex, focus, and directrix. But I'm going to show it to you 2 different ways so you can kind of see which method you like better. So example 2 is asking us to find the vertex, focus, and directrix of the parabola y equals 2x squared plus 4x minus 1. And they're saying do this by completing the square and without completing the square. And they also want us to find out if the parabola is opening up or down. Let's take a look at this guy over here. So we are given y equals 2x squared plus 4x minus 1. So the first method we will do is completing the square. And so we had again talked about this in chapter 3, but just in case you don't remember, we start by taking the first two terms of our equation over here, and we are only going to factor out the constant. So you can see I have 2x squared and 4x, so between 2 and 4, I need to take that 2 outside because my leading coefficient should only be 1. So we definitely need to take that 2 outside. So 2x squared, and luckily in this example that 2 goes into 4 evenly, which will leave us behind with 2x, and then minus 1 at the end would stay as it is. So our goal is basically to get rid of this 2, bring it on the outside, and then factor out what you can with the x squared and the x term. That constant term stays outside, so that guy will stay as it is, as -1. Right now, once you have taken that 2 outside, we look inside the parentheses, that's the x squared plus 2x, and we want to complete the square just for the parentheses part now. So we're going to take the coefficient of the middle term, which is our 2, and remember this is where we divide that by 2 and square it. So 2 divided by 2, of course, is 1, and 1 squared would obviously just be 1. So what happens is once you figure out this 1, inside the parentheses, remember we add that 1 and subtract it at the same time, so that we are basically maintaining the balance of our equation. We're not really changing the equation, we're just taking it from the standard form into the transformation form. For a perfect square trinomial, we just need these first 3 terms, which means that -1, we want to bring it outside of the parentheses. So remember, to bring it outside of the parentheses, you end up multiplying this -1 with this leading term of 2 over here. So you would have that 2 will stay, x squared plus 2x plus 1 will stay, and then this -1 multiplied with the 2 in the front will become -2, and this is how you bring it outside of the parentheses. Okay, so now that we got rid of that -1 and brought it outside and it became -2, we have a perfect square trinomial inside our parentheses now. So you can go ahead and factor this, go ahead and combine these last 2 terms. And what does x squared plus 2x plus 1 factor into? Remember, you are looking for 2 numbers that multiply to 1 and add up to give you 2. Very nice, Jack. Yeah, it's going to factor into +1 and +1. 1 times 1 is 1, 1 plus 1 is 2. So this guy will factor into x plus 1 squared. Obviously, when we add -2 and -1, we end up getting -3. So what the completing the square is basically doing, is taking our standard form of the equation and converting it into the transformation form. And we are doing this because now we can identify, of course we could identify A before, we can identify H and the K values once you convert it to the transformation form. So as you can see over here, our leading term on the outside, that 2 is going to be the A value. The H is coming from the parentheses. Now, since this is x plus 1, that actually tells us the H value itself is -1. K is going to be that constant at the end. So since that's -3, of course, our K value is also going to be -3. So you can see our vertex for the parabola is going to be at -1, -3. A here is a positive number, so that tells us our parabola will open upwards. And if the parabola opens upward, then remember your focus is going to be above the directrix. So at -1 and at -3 is where we have the vertex. So the focus has to be above the vertex and directrix has to be below it because this is a parabola opening upwards. So remember, for our focus, the ordered pair is going to be h comma k plus p, and our directrix is going to be the equation y equals k minus p. So we have the h and k values. What we are missing again here is that p value, and that p value is going to come from this relationship of a. So let's start by finding the p value first. So remember, the relationship is a equals 1 divided by 4p, and we know our a is 2, so this will be 2 equals 1 divided by 4p. So can you work backwards and tell me what the p value will come out to be in this case? Okay, Audrey, I just saw your message. Very good for that factoring. No, it does not come out to be 8. Okay, Jack, you've got 1/6, 1/8. Yeah, it actually will come out to be a fraction answer. So what's going to happen here is you would multiply both sides by 4p. Because, of course, we want to get it out of the denominator first. So 4 times 2 will give us 8p equals 1. And then, of course, to get p by itself, we would go ahead and divide both sides by 8. So yeah, as you can see, we end up getting p equals 1/8. All right, now that you have found the p value, all you have to do is put it into these two different formulas to come up with the focus and the directrix. So let's do the focus first. So we want to find k plus p, and again our k value was -3. So -3 plus 1/8 will give us what? And we will leave these answers as fractions again. So -3 plus 1/8 will give us You guys don't have an answer yet? -24/8. That's not what I came up with. Because we would have to multiply this with 8. And that would end up giving us -24/8 plus 1/8, right? Yeah, that's good. Yeah, -23/8. All right, Lori and Morgan, very good. So -23/8. So again, remember your focus is h and k plus p. So our h value was -1. So -1 and -23/8 for the focus. And since that distance p is only 1/8, that actually tells us that our focus is actually going to be very close to our vertex, because you're only talking about a distance of 1/8. So they're almost going to be, touching each other if you think about it. Now, since that distance is 1/8 for the p-value, that also tells us our directrix has to be going down, pretty close to our vertex again. So that's just going to be that distance of 1/8. So again, using the same definition for our directrix, you basically need to find what k minus p is. So same calculation you did here, except it's going to be -3 minus 1/8. So obviously, you would still do the same thing, find your common denominator, and what would this end up giving us? If you got -23/8 for the y coordinate for the focus, this guy you are subtracting. Yeah, very nice, Lori. Morgan, yeah, you're going to end up getting -24 minus 1, which would be -25/8. Alrighty, very nice. And again, let me remind you that the directrix is again going to be an equation since this is a line. So our directrix comes out to be y equals -25/8. So they were asking us to identify the vertex, the focus, and the directrix. So we've got our vertex right over here when we came up with our h and k values, because of course the vertex is h comma k. And then once you found that p value, using the relationship between a and p, then we could come up with what the focus and directrix is. Now, this process of finding the focus and the directrix is going to stay the same, no matter if you used completing the square or you do not use completing the square. So the only difference is when we used completing the square, then by looking at the transformation form, we came up with our h and k values. And so then we were able to, move forward with the focus and directrix. Now, they were also asking us to try and solve this without using completing the square. So without completing the square, and we have seen this process before. So if you don't want to use completing the square, then basically you have to use, for finding the vertex of our parabola, remember we have the equation x equals -b/2a. And then you plug that back into your function to find the y value. So for the y value, we put whatever x you get from here into our function and calculate the y values. If you wanted to leave your equation in the standard form, which was again given to us as y equals 2x squared plus 4x minus 1, we can find the vertex of our parabola by using this equation, -b/2a. So this is our a value, this is our b value. So that would be -4/2 times a, which is also 2. So basically -4 over +4, which would give you -1. And then put this back into your function to find the y value. So 2 times -1 squared plus 4 times -1 minus 1. Let's see, -1 squared would become +1. So +1 times 2 is +2. 4 times -1 would be -4, and then -1 over here. Let's see, 2 minus 4 is -2. -2 minus 1 is -3. And you can see we got the same values, -1 and -3. So the vertex of our parabola is going to be -1 and -3. And remember, these give us our h and k values. You already have the a value from here. So you've got A equals 2, H equals -1, K equals -3. Now, once you have these H, K, and A values, like I said, finding the focus and the directrix, it's still going to be the same. So we would still have to come back to this step, find our P. Once we found the P value, we would come back and find our focus and find our directrix like we did here. So the only difference between using completing the square is when you did completing the square, we were able to identify our AHK values by looking at the equation. If you don't use completing the square, then you are using this vertex formula. That helps you come up with the H and K values for your vertex. And then again, you're back to finding your focus and directrix. So that part doesn't change. So like I said, use whichever method you are more comfortable with. If you don't want to do completing the square, then go directly into your vertex formula. If you are comfortable with completing the square and you want to go that route, you can. But this would be the process where your equation is given to you in the standard form, and they're asking you to find the vertex, focus, and directrix of your parabola. And you know, like I said, since we knew our A value was positive, we also knew that our parabola was opening upward. So this was also one of the questions they wanted us to answer. Questions on this one, guys? Alrighty. The next part we are talking about is graphing these parabolas. So according to the geometric definition, every point on the parabola is equidistant from its focus and directrix. So let me just talk about that a little bit here. So what they are basically saying is if you take a distance, let's say we have this point over here. If you take the distance of this point from the focus and the distance of this point from the directrix, that distance is going to be the same. So this distance here will be the same as this distance here. And this is true for all points on that curve of our parabola. So that's what they are saying, that all points in the plane of your parabola are going to be equidistant from the focus and the directrix. So, you know, of course, when we are talking about graphing these, again, we need to know the vertex because that tells us which is the highest or the lowest point on our graph. So we want to find the focus, axis of symmetry, the X and Y intercepts, and they are, as you can see, giving us the focus and the directrix, and they want us to draw the graph, but also show where the focus and the directrix are going to be. Now, since we are talking about graphing these, it will make sense to find what the decimal approximations of these points are going to be. So, you know where on the graph those points will fall. So can you tell me what the decimal approximation for 35/4 is going to be? And the decimal approximation for 37/4. Okay, so 35/4 is 8.75. Okay, and then for 37/4, yeah, 9.25. Okay. So let's see. I've got -1, 1, 2, 3, 4, 5, 6, 7, 8, and 8.75 would be right over here. Directrix is the line, y equals 9.25, so just a quarter above, and this is where my directrix is going to be. So the reason why I'm graphing this is to show you that your focus is below the directrix, so that actually tells us that our parabola does it open up or down? What does that tell us? Yeah, very nice, Lori. It's going to open downwards because your focus is below the directrix. So the parabola opens downwards. So remember, this tells us our A value is going to be negative, which means our P value is also going to be negative. Okay, so let's try and gather all the information we can from this. Alrighty, so we are given the focus at negative 1/35/4 and directrix at y equals 37/4, which is basically 9.25, and this guy would be negative 8.75. We also know our parabola opens down. So A is negative and P is negative. Alrighty. Now, your vertex we know is going to be passing through that same coordinate of -1, but we need to find out what our K value is. So again, if you think about this, we have K plus P, which comes from the focus, and that is 8.75. Our K minus P, which comes from the directrix, is 9.25. So any idea what the P value should be here? Now remember, you can do the calculation, or you can try and think of this in terms of, you know, what's going to be the halfway distance between 8.75 and 9.25. So any idea what our K value or our P value should be? So what do you think? 8.75 and 9.25. Okay, so what you want to do here is take the difference between those two numbers and divide it by 2. That's it. What answer will you come up with? Okay, Audrey, no problem. So 9.25 minus 8.75, and then divide that answer by 2, what you get? Yeah, very nice, Meredith. And yeah, Morgan, you're giving me the K value. So if you just take the difference between 9.25 and 8.75, that will give you a difference of course, half, 0.5. And then when you divide that by 2, it gives you 0.25, or basically a quarter. So that actually tells you the distance between the vertex and the focus, or the vertex and the directrix, is basically 1/4. So your p-value is going to be 1/4. And that, of course, tells you then if I add 1/4 to, sorry, it will be negative 1/4 because we did say our parabola is opening downward. So p is going to be a negative value. So your p is going to be negative 1/4. So when I take k plus p and get 8.75, that means my k value actually has to be 9, so that when I add the negative 1/4 to it, I get 8.75. When I take k minus p, which gives us the directrix, that's k minus negative 1/4, it gives us 9.25. So you can use that idea, or like I had told you before, solve this system of equations, and that will also give you the same result. So k comes out to be 9, p value comes out to be negative 1/4. So our vertex is going to be hk, negative 1, positive 9. And if you look at that on our graph over here, it is, and again, this guy will be a little bit harder to graph in here. But basically, it's going to be right here at negative 1, 9, where we are going to have the vertex of our parabola. And just again, 1/4 below it is the vertex, 1/4 above it is going to be our directrix. Okay, so now that we have the vertex, we of course still need what our x and y intercepts are going to be, and see what that graph looks like. Now the axis of symmetry, again, if you remember our characteristics from chapter 3, your axis of symmetry will again always pass through the vertex, and in this case it passes through the vertex and the focus. So your axis of symmetry is going to be x equals -1. So it's basically using this x coordinate from your focus and your vertex. So the axis of symmetry is going to be at x equals -1. We already have our vertex. Now, how can we come up with the x and y intercepts for this parabola over here? Because all we have is the directrix and the focus, and now we have the vertex and the axis of symmetry. So is that enough for us to be able to find out where the x and y intercepts are going to be? Or what would be helpful for us to find the x and the y intercepts? What should we do next? Because I don't think we have enough information to find the x-intercept and the y-intercept. So what do we need to help us find the x and y-intercepts? Nobody? Come on, guys, you've done the x and y-intercept calculations in other chapters, so you should know what we need to find the x and y-intercept. Don't we need an equation? Because how are you going to find the x and y intercepts without an equation? So we need to know what the equation of this parabola is going to be if we're going to find the x and y intercepts. And you have all the information you need here. You've got your h and k values from the vertex. You know your p value is -1/4. So if you just work backwards, you can go ahead and find what the equation is going to be. So using the p-value, find the a value, and then you have your equation in the transformation form. So we need to find our a value next, which again is going to be a equals 1 divided by 4p. We of course know Lori, you've got x plus 1 and x minus 9. I'm not sure because that, obviously wouldn't be the quadratic equation. So I don't know if you're giving me the factor form or what, because that's not going to be our equation. Okay, let's take a look at it and see. So our p-value, remember, is -1/4. So since you have 4 on the top and 4 on the bottom, these 4s can cancel each other out, leaving us behind with 1 divided by -1, which basically gives you an a value of -1. So we have in the transformation form everything that we need. So a is -1, x minus our h is also -1. So negative and negative would actually become +1 squared. And then our k is +9. So basically you have negative x plus 1 squared plus 9 as the equation of our parabola. And once you have this, you can find your x-intercepts and your y-intercepts. So for the x-intercepts, make the y value 0. For the y-intercept, make your x value 0. So let's do the y-intercept calculation first because that goes a little bit quicker. And then we'll come back and do the x-intercept. So for the y-intercept, we are taking our x value and setting it equal to 0. So can you tell me what that y-intercept comes out to be? So Lori, coming back to what you had on your chat, you can see that x plus 1 is definitely going to be part of the equation, but that x minus 9, I'm still not sure, kind of what you were thinking about that. Because we do have a positive 9, right? So that sign will stay the same. It will stay positive. So what do you get for the y-intercept? Yeah, very nice, Deborah. Because you would have 0 plus 1, which is 1. 1 squared is 1. So basically you have -1 from that first term, plus 9, which would end up giving you 8. So your y-intercept will actually be the point 0.08. And when we graph it, that 0.8 is going to be right over here. So basically your graph will be going like this, and using symmetry, we know it will be going like this. So now we want to know where on the x-axis our parabola would be crossing. So that's going to be our x-intercepts, which is where we make our y value 0. And you have negative x plus 1 squared plus 9. And we are trying to, of course, get our x by itself. So you can start by subtracting the 9, move it to the other side. So you get -9 equals negative the quantity x plus 1 squared. You can get rid of those negative signs. So divide both sides by -1. So we have +9 equals x plus 1 squared. Now what are we going to do? So to get x by itself, what should we do? Come on, guys, you should know how to solve these type of equations at this point. And for those of you who are showing me your ceilings, I really don't want to see your ceilings. I want to see you. So if you would please turn your camera to yourself, because the idea is I need to be able to see that you are in attendance with class. Okay, Jack, you've got x equals 2 and x equals -4. Deborah, looks like you came up with the same answer. Okay, let's check that really quickly. Meredith, you've got +2. So again, remember, anytime you end up taking a square root on your equations, we always get one positive and one negative root. So what happens in this case is square root of 9 is 3, and that becomes positive and -3, and then we get x plus 1 over here. So when you subtract that 1, you're going to come up with two different answers, because you would have +3 minus 1, or you would have -3 minus 1. So that would basically end up giving us x equals +2 or -4. So as ordered pairs, that would be 2, 0, and -4, 0 for our x-intercepts. Okay, so we've got our y-intercept over here, 0, 8, and then x-intercepts at 2, 0 and -4, 0. So that would end up looking like 2, 0 here, -4, 0 over here, and then of course just complete your parabola. Oops. And this is what that graph of the parabola would end up looking like. So we have our vertex, we have our axis of symmetry, we got our x and y intercepts, and then we were kind of trying to show our focus and directrix, but obviously on this graph it doesn't quite show up as nicely because they are so close to each other, but you can kind of see them over here with our focus. Hold on. So our focus is going to be at -1 and 35 over 4. Okay. So again, this is very similar to what you did in example 1, but they gave you the focus and the directrix and asked you to come up with the equation of your parabola. So, of course, using the focus and the directrix, we need to come up with our P and the K value, which then helps us find the vertex. Of course, axis of symmetry passes through the x coordinate. So that can be the x coordinate of the focus or the x coordinate of the vertex. Once you know the P value, you can work backwards to find the A value. And that, of course, led us to the equation of our parabola. And then we were able to come up with what our Y and X intercepts are going to be, and then complete our graph based on that. So you will see here, we're not using that X and Y table like we normally do for graphing, because, obviously they want us to use a little bit of a different information over here. This one here, so far we have looked at parabolas opening up and down, but if you were looking at parabolas opening left or right, then, you can imagine some of these definitions are going to change, because you can have, y equals 2x squared, which is a parabola opening up, or you can have x equals 2y squared, which would be a parabola opening to the right. So they're basically saying by interchanging the variables, you're basically interchanging the roles of your x and y axes. So like I said, this equation y equals 2x squared will open up, but x equals 2y squared opens to the right. So for parabolas opening left or right, your directrix will obviously now become a vertical line. If the focus is going to be to the right of the directrix, then of course your parabola opens right. If the focus is towards the left of the directrix, your parabola will open to the left. Since we are interchanging the roles of x and y, you can see how the equation of our parabola is also going to change. It becomes x equals a times the quantity y minus k squared plus h. So x and y are switching places, but you should see the h and k are also switching places in that equation. In the standard form, your equation would look like x equals ay squared plus by plus c. Same thing, if a is positive, your parabola would be opening to the right. If a is negative, parabola opens to the left. Again, because our roles for x and y are changing, this formula of negative b over 2a will now give you the y coordinate of the vertex, which will also give you the axis of symmetry for our parabola. And obviously this time your axis of symmetry will end up becoming a horizontal line. And you can kind of see with these graphs over here, your axis of symmetry would now be passing through the focus and the vertex as a horizontal line. Your directrix has now become a vertical line. And look at these equations for the directrix. It is now x equals h minus p. Our vertex is still going to be hk because we are still writing our ordered pairs as x and y. So the vertex is still hk. But this time you will notice we are adding that p value to our x coordinates. So it's h plus p for the focus on the x coordinate, and the k value stays as it is. And your directrix became, as I just showed you, x equals h minus p. And then of course you can see the general form of our equations over here. So just very quickly, we're keeping it to a graphing. They are giving us the equation of the parabola, and they're asking us to find the vertex, axis of symmetry, again, x and y intercepts, and the focus and the directrix, and asking us to graph, using those two values also. So let's see, we are given the equation of our parabola, which is x equals y squared plus y minus 6. So you can see that coefficient on the y square is a positive 1. So that's actually going to be our a value. So we can say a equals positive 1, which is of course a positive number. That means our parabola is going to open to the right. And again, since we do have that relationship between our a and p values, that also tells us that our p value has to be positive. And graphically, that also means our focus is going to be to the right of the directrix. So let's go ahead and see what all information we can gather out of this equation that's given to us over here. So since this is given to us in the standard form, what I'm actually going to do is start by finding our vertex by using this negative b over 2a. And remember, this time that will give us the y coordinate. So let's start by finding the vertex of our parabola, and y equals negative b over 2a. So can you tell me what this y value comes out to be? And again, remember, this will be our a value, and the coordinate here would be our b value. So what do you get as, you can give me the y value for the vertex, or you can give me the entire vertex, whatever you have calculated. Okay, Morgan, you've got -1 and +1. Okay, that's not what I came up with. Because your B value is also going to be +1. You would have -1 on the top and then 2 times 1 on the bottom, which would end up giving us -1/2. So the y coordinate for our vertex is coming out to be -1/2. And then you would take this and put it back into your equation to find the x value. So that would have to be x equals y squared plus y minus 6. So Morgan, what do you think happened here?
No, so I meant that that's what you would put in the parentheses, but I didn't see the negative to the left of the parenthesis.
Okay.
So -1 on the top and then the 2 times +1 is what I meant.
I see. Got it. Got it. Okay. Thank you. All right. I kept wondering why you got those answers. All righty. So what are you getting for the x value for this vertex then? Because, you know, when you do the -1/2 squared, of course, negative times negative would become positive. 1 times 1 is 1. 2 times 2, of course, would be 4. And then positive and negative in the middle term would, of course, just become -1/2. And then -6. And you can kind of think of that as being 6/1. So what will you get when you simplify this? Again, you can throw this into your calculator or you can try and find common denominators for all of them. Okay, Morgan, you've got -25/4. Lori, you got the same thing. Yeah, because you can do 4 as your common denominator. So when you multiply all of these, you basically end up getting 1/4 minus 2/4 minus 24 over 4. So of course, all of that would then become, you know, keeping that common denominator, you have 1 minus 2, which is -1. -1 minus 24 is -25. So you should basically have -25/4 as your final answer. So this will now be our x value. So -25/4, which is obviously not a very happy number. So as a decimal, just so we know where to graph it, it will be -6.25. And then of course the -1/2 would be -0.5. So let's see, -6.25. So that would be 1, 2, 3, 4, 5, 6. -6.25 and -0.5 somewhere over here. So that's our vertex. I'm keeping it in decimals here so you know where we have graphed that vertex. Now, when we talk about axis of symmetry, remember your axis of symmetry is now a horizontal line which passes through y equals, again, the -b/2a. So after you have found your vertex for the axis of symmetry, we are going to use the same calculation of y equals -b/2a. So that's going to be the line y equals 1/2, since we've already done that calculation. So your axis of symmetry would basically then be this horizontal line, passing through that y equals negative 1/2. So that's our axis of symmetry over here. This, of course, is our vertex right over here. All right, so we've got the vertex, we've got the axis of symmetry. Now let's go ahead and see what the focus and directrix and those two intercepts are going to end up looking like. Okay, so let's come back over here. And do we have enough information for our equation yet? Well, actually, we do have an equation in this example. So we can find our x and y intercept. So let's do that first. For our x-intercept, we would need to make our y value 0. So since we already have the equation, that is x equals y squared plus y minus 6. Yeah, y squared plus y minus 6. So that would, of course, end up becoming just negative 6. So our x-intercept would be at negative 6, 0. So and again, let me make this guy a little bit bigger here. So at negative 6, 0 is literally this point right over here, because at negative 6.25 is where we have our vertex. So literally just a quarter of a distance to its right, and then of course at 0. So we know this graph is going to be going somewhere like this. And with symmetry, we would have this point below it. So our graph would be going in this direction. Now we need to know where it's going to be crossing the y-axis at. And of course, since this is a parabola opening to the right, we should have two different points on the y-axis where our graph would be crossing it at. So for the y-intercepts, we are going to make our x value 0. So that would be 0 equals y squared plus y minus 6. Can we factor this? Two numbers that multiply to give us negative 6 but add up to give us positive 1. Positive 3, negative 2, okay. So Jack, let's see. When we multiply 3 and negative 2, we get negative 6. When we add 3 and negative 2, we get positive 1. Very nice. So you can factor this guy into y plus 3 and y minus 2. Take each factor, set it equal to 0. And you have your y-intercept. So this guy here will give us negative 3. So that's 0, negative 3 as our y-intercept. And this guy, of course, would give us y equals positive 2. So again, 0, positive 2 would be our y-intercept. So let's see, 0, negative 3, and 0, 2. And that would be at 0, negative 3, 0, 2. So this graph would be going this way. This graph would be going this way, or the arm. Okay, so once we have our x and y intercepts, the only thing left to calculate now is our focus and directrix. So again, remember for our focus, and I'm looking at this graph on the left-hand side since that's a parabola opening to the right. Our focus is going to be h plus p comma k. And then of course directrix is defined as, you know what, let's do this. directrix again is defined as x equals h minus p. Now remember, our h and k values you can get from the vertex of your parabola, and we already have the vertex of our parabola, so we know we have the h and k from here, or you can think of the h and k from here. So our h is negative 25 over 4, and k is negative 1/2. So h plus p would be negative 25 over 4 plus, I guess we do need to figure out what that p value is, and k is given to us as negative 1/2. For this guy, h minus p, we will need to calculate negative 25 over 4 minus p. So again, does anybody know what the p value is? Because you already have the a value given to us as 1. Since we know that our a and p have the same sign, we know p is also going to be a positive number. So you just need to plug this into your formula of a equals 1 divided by 4p, and you can come up with that p value. So what is our p value going to be here? A is 1. So what do you think that p comes out to be? So what did you guys get for p? Shouldn't be too hard since you don't have a whole bunch of numbers here you need to work with. So what do you get for p equals what? Very nice, Lori. Yeah. Because honestly, all you need to do is go ahead and multiply both sides by p. So the p variable would cancel out, and you would end up getting p times 1, of course, is p, and then you are left with 1/4 over here. So your p value would come out to be 1/4, and then all you are doing is adding 1/4 to the focus and subtracting 1/4 from the directrix. So what is h plus p coming out to be, and what is h minus p coming out to be? Okay, Deborah, very good. Meredith, very nice, 1/4. So h plus p gives you what? Okay. Audrey, negative 6.5. So what's negative 24 divided by 4, guys? Because 4 goes into 24 evenly. So yeah, what do you get? Negative 6. Very nice. So you would end up getting negative 6. So this would actually then end up becoming the ordered pair -6 and -1/2 for the focus. And then what do you have for the directrix here? H minus P. Yeah, it will become -26 over 4, which of course would reduce down to negative. Let's see, both of them can go by 2. So -13 over 2. So that would become our directrix. So x equals -13 over 2. And so when we bring this over, focus is at -6, -0.5, and then directrix would be x equals -6.5. So again, graphing this would be a little bit interesting, -6 and -1/2. So technically our focus would be this point right here, which would be right underneath that x-intercept, and then at -6.5, we would have our directrix. So directrix is at x equals -13 over 2, and our focus was at -6, -1/2. But yeah, it's kind of hard to see because again, they're so close to each other. But this at least kind of gives you an idea of how those x and y values interchange when we go from a parabola opening up and down to a parabola opening left or right. So you can just kind of see in this paragraph over here how all of those definitions kind of change. Okay. Alrighty, so now that we have looked at the graphs and we have looked at their geometric definition, one of the common applications that we actually use for these parabolas or any of these conic sections are actually their reflection property. We are actually interested in how these parabolic surfaces, what that reflection for them looks like. So they're talking about, back in chapter 3, we talked about, how maximizing or minimizing data could help us with our needs. We had talked about creating the maximum area for a garden. We had talked about, also that archer example when he shoots an arrow, and you guys had a bunch of other examples in your homework as well. But now, like I said, we are more interested in the reflection property of a parabola. So we are talking about when a ray of light traveling parallel to the axis of symmetry. So this is of course talking in terms of when your parabolas are opening right or left. So your axis of symmetry, remember, is this horizontal line. So if you think about the axis of symmetry here, that would be the line which would be passing through the vertex and the focus. So if you have light which is traveling parallel to the axis of symmetry and it hits that parabolic surface, which would be a parabolic reflector, and that's of course this curve in the red, what happens is that ray of light will hit that parabolic reflector, and as you will see, it starts going towards the focus. So all of these rays of light are hitting our reflector, and then it gets reflected back towards the focus. So you've got the ray of light coming from this direction, it hits the reflector, and you will see it again starts concentrating towards the focus. And we actually use this property in telescopes. But you can also think of this same concept being used, as I mentioned, telescopes, but you are also thinking about spotlights. But what's happening in a spotlight is we're doing it in the reverse direction. So your light source is going to be at the focus. So what happens is, in this case, and just a rough sketch over here, if this is your spotlight, So basically what it's doing is the light is now getting reflected towards that parabolic reflector, and then it goes out where you want to focus it. So the light will now hit the parabolic reflector and then go out and, you know, focus on whatever object you want that spotlight to be focused on. So it's the reflective property being used in reverse. The same idea of the light, like spotlights, you can also think of your flashlights, you know, the ones you normally keep in your home or your cars. So flashlight kind of uses the same idea, but we can use this reflector property also in telephoto camera lenses, you know, radio antennas, satellite dishes, eavesdropping devices. I mean, your radio antenna, satellite dishes, and eavesdropping devices, you know, basically they all look like that satellite dish with that little receiver, which is always placed at where the focus of that parabola is going to be. And so that way, you know, the light or sound coming from a distance will then bounce off that parabolic reflector surface that these satellite dishes would have, and then they get reflected towards the focus where that receiver is going to be. And, you know, that's how we get our signal for, you know, think about your satellite dishes. If you have like cable, not cable, but, you know, like a dish service at home for your television, that's kind of the concept that goes into play. So, you know, of course, Hubble Space Telescope is one of our most famous space telescopes out there till the James Webb telescope is launched. I think early next year, I think is when they're thinking of launching it. So they're talking about how the Hubble Space Telescope uses a glass mirror with a parabolic cross section. It has a diameter of 2.4 meters. So you can see if we take this axis of symmetry in the middle, then that 2.4 meters kind of gets broken up into 1.2 meters and 1.2 meters on each side of our axis of symmetry. They're telling us the focus of the parabola is at 57.6 meters from the vertex. So this 57.6 meters from the vertex is actually that distance P that we keep talking about. So that's this distance between the vertex and the parabola, which is our 57.6 meters in this case. Now, I don't know if you guys have heard this story or not, but when they first launched the Hubble Space Telescope, they were actually getting back really blurry pictures. They were not clear, distinct pictures that we're so used to seeing coming out of the Hubble Space Telescope. And part of that was when they manufactured that mirror with the parabolic surface, it was off by literally like micrometers, but it was off enough that, you know, that light that was getting reflected, and with that focus being at 57.6 meters, they were actually not able to get that right focus distance. So the telescope was not reading those images in clarity. So they actually had to have a second mission where, you know, obviously astronauts went up and they actually installed a second mirror to kind of create the accurate distance that they needed for us to get those nice, clean, crisp photographs. So if you actually go and research the Hubble Space Telescope when it was first launched, you can see, you could basically just see blobs of light. They did not look like anything much because it was such a blurry image. So, you know, I mean, these calculations have to be so precise if you're actually going to get, you know, good use out of these telescopes over here. So we're kind of looking at a example here for the Hale telescope, which is, you know, on the Palomar Mountains in California. They're telling us the focus for this Hale telescope is at 55 feet above the mirror, which is at the vertex. So that's actually telling you what the distance between the focus and the vertex is going to be, which is 55 feet. And you can see that right over here. They're telling us the Pyrex glass mirror is 200 inches in diameter, which means the whole diameter of that Pyrex glass mirror is 200 inches. They're telling us the thickness of the glass mirror is 23 inches in the center, which means they're talking about this thickness of the glass here, which is 23 inches. they want to know what the equation of the parabola is that was used to shape the glass. So that's that red line you can see in the image of your uh, here's, I guess, the telescope over here. So they basically want to know what is the equation of that parabolic surface, which is the red line, that was used to shape the glass. And they want to know what is the thickness of the outside edge. So that's going to be the thickness of this one. We know the center distance is 23 inches, but you can see how this mirror curves up a little bit. So you have a little bit of that extra distance. So they want to know what is the outside thickness of the glass as well. So, basically we have to see, okay, coming up with the equation of the parabola, we definitely need to know our A, H, and K values if we are going to be able to calculate any of this. But, this is a mirror on a telescope, so we can actually take a few liberties with our calculation over here. So let's take a look at all the information we have on hand. They are telling us the distance between the vertex and the focus is 55 feet. One thing you should notice is the focus is given to us in feet, but all the other calculations are given to us in inches. So if you want to keep, all the calculations in inches, which is basically what the measurement of the glass is, you probably want to convert this into inches. So just multiply this by 12 inches, and that's of course because 1 feet has 12 inches in it. What will we get as our p-value over here when you convert it into yes, Deborah, I just saw your comment. That was definitely an expensive mistake, but at least they were able to fix it because once you launch a satellite, it's kind of hard to bring it back to Earth. You normally don't bring these back, so obviously the astronauts had to go back up and fix that error. But I'm glad they were able to fix it because we have been able to explore so much of that space that we were not able to before. And obviously now they're working on an even advanced telescope with the James Webb telescope. Alrighty, very nice. So when you multiply 55 into 12 inches, yeah, Lori, we get 660 inches. So that's telling us, that distance between the focus and the vertex is 660 inches. Alrighty, so we've got that taken care of. And let me do a little bit of a rough sketch over here. So let's say these are our X and Y axes. And we know we've got our parabola, which is the surface of our glass over here. Let's say, and of course this is not a good distance, but that's our focus. We know this distance between the focus and the vertex is 660 inches. They're telling us the diameter of the mirror is 200 inches. Okay, so if this is our mirror, we know this diameter is 200 inches. So if we think of the y-axis as passing through the vertex and the focus, that means 100 inches of our glass is going to be on the right-hand side, and 100 inches of our glass is going to be on the left-hand side. We also know the center thickness of our glass is, I believe it was 23 inches. Yeah, 23 inches. So we know this thickness. Now they are asking us to find out what the outside thickness is going to be. And of course, we need to know what the equation of our parabola is going to be. So the liberty that I was talking about is basically, you can imagine if we take this parabolic mirror of our telescope and put it on this X and Y axes, you can actually imagine that the vertex of our parabola can be at the origin. So you can think of that vertex being at 0, 0, because we can place the vertex wherever we like, and that would make our calculations a lot easier. So just imagine the vertex of this parabola being at 0, 0. So that would, of course, give us our H and K values. we already know what P is. We know P value is going to be 660 inches. So then you can work backwards to find out what that A value is going to be, because, of course, we need to know the A value to come up with the equation for our parabola. So that would end up being 1 divided by 4 times P. And we know the P is going to be 660 inches. So that would give you what the A value is. And what do we come up with? Okay, Jack, I just saw your message. Let me see. We would also have to add 23 inches to the 55 feet because it says it's 55 feet above the mirror, which is okay. But Jack, what's going to happen here? And let me show you that. You would need to add the 23 inches if we were assuming the vertex is down here at the bottom of the mirror. But your parabolic surface is only going to be on the upper part of your graph. So that means your vertex is actually going to be right on that top of that parabolic surface. So you're actually going to be above that 23 inches. So you actually don't have to take that into consideration. Does that make sense? Okay, very good. Alrighty, and then you guys came up with 1 over 2640 for the value of A. That's good. All right, so let's see. All right, so we've got our A value. We are assuming the vertex being at 0, 0, so that gives you your H and K value. So for the equation of our parabola, you've got, again, in the transformation form, y equals A times x minus h squared plus k. So we've got A at 1 over 2640. We've got x minus h is 0. K is 0. So you basically end up getting x minus 0 would, of course, just be x squared. And that plus 0 will actually disappear. So you just have y equals 1 divided by 2640 x squared, and that would be the equation of the parabola, which would be the shape of our glass mirror for this Hale telescope. Now, the other thing they asked us to find was the thickness of the outside edge. And finding that thickness of the outside edge is basically, if we know, I'm kind of running out of my colors over here, but if we know this is our parabola, then this point over here is basically the y value when you know your x value over here. So think about this. This distance here is 100 inches. So you can think of this x value, because obviously this is all in line. So you can think of this point here having the x value of 100, and we just want to know what that y value is. So once you find your equation for the parabola, to find this point, all you have to do is take your x to be 100, which, technically, how about I do it on this side? So we know our x value here is going to be 100. We just want to find what our y value is, which will actually give you, let's get rid of it so you don't get confused here, which will actually give you this distance right over here once you find that. So by finding this y value for this coordinate, it basically gives you this distance. And when you have this distance, then we can add the 23 inches for this bottom part here, and you would have that total thickness of your glass mirror. So the first thing we have to do Okay, so the first thing we are going to do is take x equals 100 and find the y value. So that would be y equals 1 over 2640 x squared, which would end up coming out as 100 and 5 divided by 2640. So 1 over 2640 x squared, which would end up coming out as 100 and 5 divided by 2640. 1 over 2640 x squared, which would end up coming out as 100 and 5 divided by 2640. 1 over 2640 x squared, which would end up coming out as 100 and 5 divided by 2640. 1 over 2640 x squared, which would end up coming out as 100 and 5 divided by 2640. 1 over 2640 x squared, which would end up coming out as 100 and 5 divided by 2640. 1 over 2640 x squared, which would end up coming out as 100 and 5 divided by 2640. 1 over 2640 x squared, which would end up coming out as 100 and 5 divided by 2640. 1 over 2640 x squared, which would end up coming out as 100 and 5 divided by 2640. 1 over 2640 x squared, which would end up coming out as 100 and 5 divided by And I think we will leave them in decimals because I'm not sure we really want to do these as fractions. So what kind of y value are you looking at here for x as being 100 inches? So 100 squared multiplied by 1 divided by 2640. So what do you end up getting for this y value here? Okay, Deborah, so as a decimal, what do you think that one would end up looking like? Okay, so let's see, you've got 3.78. Your fraction was 125 over 33. And then you said repeating 3.7878. Okay, so we'll just round it to, I guess, 2 decimal places. Okay, so remember that 3.79 is going to be this distance over here. And obviously my graph is not to scale, so it doesn't look like it should be 3.79 if that is 23, but you get the idea. So this thickness just from the upper half is going to be 3.79, and then as I said, you need to add that extra 23 thickness. So the total thickness would then come out to be the 3.79 inches plus the 23 inches, and of course that ends up becoming, what is that, 26.79. If they wanted to 1 decimal place, you can do 26.8. And again, this will depend on rounding rules. So I'm just kind of leaving it, in different options, just depending on what the rounding rules will tell you. Of course, if we are talking about the mirror on a telescope, precision is going to be a big deal about it. So they probably will do more decimal places than what we have over here, because you obviously don't want to mess up on that thickness of your mirror. So anybody who has a question, because I know this was a couple steps that were involved over here, because first we came up with assuming that the vertex of our parabola was at 0, 0, so we could get those h and k values. Using the p value, we worked backwards to calculate our a. Once you had the a, h, and k values, we were able to come up with the equation of our parabola. Now, since we are again assuming that the center of our mirror was on the y-axis, we said 100 inches were going to be on both sides. So that gave you how you could come up with this point over here for our y value. So we used 100 inches as the x value, and then use that basically to find out what the y value would be, which gave us the upper part of the mirror, what that thickness would be. And then adding that to 23 inches, you can of course see we were able to come up with that outside edge thickness of our mirror. And we're saying approximately 26.79 or whatever rounding they want us to use. And that's basically how you come up with the equation for these parabolas on a telescope. Okay, I believe that was the last example. So anybody have questions on that? So again, remember, we are focusing more on the geometric definitions over here. So when we look at the circle and ellipses and hyperbolas, again, that's going to be our main focus for, looking at them in the geometric sense. And then again, we'll also talk about what kind of reflective properties these different shapes also have. So that will again kind of be an interesting thing to talk about. So today you guys are finishing chapter 5 assignments. Again, remember, you have till midnight. You have the password for your exam. So make sure you get that taken care of. And then we will finish chapter 7 probably by Tuesday of next week. So we can use that Wednesday as a review day. And then your final will be the following week on that Monday, which I think is the 3rd, if I'm not mistaken. Yeah, it's going to be the 3rd of August. So you guys should have your practice final exam also available in my math lab. So, start finishing up your, get done with chapter 5, start with chapter 7, and then next week, after we finish chapter 7, I will go back and open up all your older homeworks. So if you want to go back and complete anything that you have incomplete, you can definitely do that. Okay? All right, guys, so we'll stop here for today. Have a wonderful weekend. Good luck for chapter 5, and I'll see you on Monday morning. Take care. Bye-bye, everybody.